Now this is the third part of the design of shaft. This part here we'll be looking into further examples. So here, okay, this is the third part. So example 3. Now find the diameter of a solid steel shaft to transmit 20 kilowatt at 200 RPM. The ultimate shear stress for the steel may be taken as 360 megapascal and a factor of safety as 8. Now in this question here, you have factor of safety and the ultimate shear stress. So wherever you see ultimate shear stress, so we always need this to work out to the allowable shear stress by dividing the ultimate shear stress here with the factor of safety. And in this case is given as 8. Now then part B, if a hollow shaft is to be used in place of this solid shaft, find the inside and the outside diameter when the ratio of inside to outside diameters is 0.5. So the first part is a solid shaft and the second part is of a hollow shaft. So here we have a diagram showing us the solid shaft. Remember, the polar moment of inertia is pi d4 over 32. Now, the allowable shear stress. So we take ultimate shear stress divided by factor of safety. So the ultimate shear stress is 360 megapascal and the factor of safety as 8. So you have this formula here. So you have ultimate 360 divided by a factor of safety 8. So you have allowable shear stress of 45 megapascal. So we can use this value here for the design of shaft, not the ultimate shear stress. So based on the power transmitted, so the N here is 200 RPM, revolutions per minute. The power 20 kilowatt, that means 20 times 10 to the power of 3. Then we know that we have to find out the torque here. So the torque transmitted will be 60p power and 2 pi n, that is the speed, 200 RPM. So we have torque transmitted 954.9 Newton meter. So the diameter of the shaft, so based on the polar moment of inertia, so we have this, and this time here we put in the allowable shear stress from this 45 megapascal, not 360. Please remember, we cannot use the 360 megapascal, the value of 360, because that is the ultimate shear stress. So once we have worked out, then we can use the allowable shear stress to find out the diameter of the shaft, the solid shaft. So we have the diameter of the solid shaft at 0.0476 meter. Okay, so it is in meter. So when it is in millimeter, it should be 47.6, or that is equivalent to 50 mm, 50 millimeter. Then part B, the solid shaft now is replaced by a hollow shaft. So this is the polar moment of inertia of a hollow shaft. So for solid shaft, that is for hollow shaft here. For hollow shaft, this is not solid. For hollow shaft, that is pi d4 minus d4 over 32. Okay, so and then they have given us the ratio of the internal diameter to the external diameter is 0.5. Or you can say the external diameter is 2 times the internal diameter. Remember, this should be a hollow shaft, not a solid shaft. The second part is a hollow shaft. So for hollow shaft, so what we did is, what I've done here is, I substitute that the D here as 2 times the internal diameter. So 2 to the power of 4, so it should be 16, and D to the power of 4. So you have D to the power of 4. So then from this you have 15 D4. Okay, so based on strength relationship, we have this. So what we do is we substitute this polar moment of inertia for the J and the R here as, okay, the external diameter over 2, external diameter over 2, where the external diameter is actually 2 times the internal diameter. So you have the shear stress is equal to this. So from this, you can find out the internal diameter of the hollow shaft. That is 25 millimeter. Then by using the ratio that we have, we got that the external diameter is actually 50 millimeter. So that's all for this example. See you again. And please, if you have any problems, please put on the comment section below of my YouTube channel in the YouTube channel of my podcast. Thank you very much. Bye.